So we've made the Earth, but where's the moon? In this video, we'll talk about where we think the moon came from. We'll use geochemistry to compare the ages of the moon and Earth, and then consider different ideas about how the moon was formed. So this is a scale distance of the Earth and the moon. The moon is a lot smaller than Earth, but compared to the moons of other planets, it's actually pretty big relative to Earth's size. The gravity of the moon pulling the Earth has a big effect on ocean tides, and this will come back later in the semester. But in the previous video about the formation of the solar system, the moon didn't come up at all. So you can ask, when did Earth get its moon? And one way to address this is by asking, how old is the moon? So we can use radioactive isotopes to answer this question. This has become an essential process in understanding the origins of the solar system and the history of Earth. Remember, a few videos ago, we talked about radioactive decay and gave the example of tritium, or hydrogen-3. Tritium has a half-life of 12 years. So after 12 years, there's 50% of the tritium that was there at year 0. At year 24, or 2 half-lives, you're down to a quarter. Because we know tritium decays into helium-3, we can monitor this process by measuring the accumulation of helium-3. But if we want to study the moon, we'll need a much longer-lived isotope. So let's consider uranium. Uranium-238 is a radioactive isotope, but it's on the much more stable end of the spectrum. Its half-life is around 4.5 billion years, so it's very well suited to these types of questions about the formation of the early Earth and the solar system. Uranium-238 eventually produces lead-206. Like the tritium and helium example, lead will accumulate as uranium decays. And this process is so predictable that we can essentially flip these axes. We can use the amount of lead to tell time. So you might notice there's a big mass difference between uranium-238 and 206 lead. This is because there's a relatively long, complicated decay chain that takes uranium-238 to lead-206. The first step is the decay of uranium-238 into thorium-234. Remember that this, like all alpha decays, ejects a helium nucleus with 2 protons and 2 neutrons. This is followed by a few beta decays where neutrons are converted back to protons. So you generate uranium-234. There's a whole series of alpha decays, and then a few beta decays, alpha decays, a few beta decays, and finally one last alpha decay, and now you're at lead-206, which is a stable isotope. So this is where the decay chain stops. This series is really complicated. It's controlled by this initial decay from uranium to thorium. Remember that this decay has a half-life of 4.5 billion years. So in that context, everything else is like a blink of an eye. But this is also interesting because the decay of uranium is also a mechanism to generate helium. And actually, uranium decay on Earth is a major source of our current helium supply. Helium is so light that it eventually escapes out of the atmosphere and into space. And so radioactive decay is how we get new helium that we use for balloons, for scientific instruments, and other uses. Anyway, the total reaction is uranium-238 to lead-206. You generate 8 helium atoms as well. So now what we need is a really good container to keep this reaction in. You can imagine if this happens in an open system, or one where mass can freely exchange, it might be hard to distinguish how much the lead has been generated from radioactive decay versus how much has been mixed in there through other geologic processes. And this would interfere with any kind of age estimation based on the uranium and lead dating system. And so after thinking about this a lot, geologists have realized that this mineral, called a zircon, is just about perfect for this. Zircons are zirconium silicates, which are composed of this really positive zirconium plus 4 ion, this very negative orthosilicate ion, so SiO4, 4-. Because these charges are so high, this creates a really strong stability of this mineral. These 2 positive and negative ions are locked together very strongly, and this makes zircons really stable. They're essentially immune to the weathering reactions that eventually grind the rest of mountains to sand and dust. So this is a picture of what zircons actually look like. Here's a sketch of what they look like on a molecular scale. One of the really useful things about zircons is that they can incorporate uranium, which is also a plus 4 ion, into the chemical structure. So that's illustrated in this diagram here. You can see zirconium atoms in this blue-gray color, oxygen in red, and silicon in yellow. And here is a green uranium atom that sort of just fits right into this crystal structure. So the amount of uranium that's in zircons is typically very low, probably on the order of 1% or less. So it doesn't really impact the bulk mineral properties of zircons. But at the same time, it's very difficult for lead to sneak into this crystal structure because it's only a plus 2 ion. It doesn't fit quite into the zirconium position in the same way that uranium does. So it'll get outcompeted by better ions like uranium 4+ or zirconium 4+. These zircons are mostly forming when you have very slow cooling of magma, like you would right after the planet's formed and everything is still hot. So zircons will crystallize with uranium inside, and then as the zircons sit there, intact, not degrading at all, eventually the uranium will start to decay, and then poof, lead shows up. Now, if lead is already in the middle of this molecular cage, it can't really leave, even though it's not a perfect fit for the crystal structure. So it's still trapped. So you essentially have this perfect time capsule. The alert is the more this uranium is lost, the more this lead can grow in. And actually, because zircons are so stable, one of the really tricky things is for scientists to actually break them down in order to measure the lead contents within them. Eventually, this was figured out. We've been able to date zircons that were originally collected on the moon during the Apollo landings, as well as key places on Earth. The age of these lunar zircons is around 4.51 billion years old. Now, it's much easier to collect zircons on Earth, and this has helped determine the age of mountain ranges and other big geological events. But the oldest zircons on Earth, which have been found in the Jack Hills of Australia, are dated to around 4.4 billion years old. And actually, there are parts of Greenland and the Canadian Arctic that are similarly old, around 4.2 billion years or so. And so this is probably the age when continents first formed. Finally, you can use these same principles to date the age of different meteorites that crash to Earth. Many of these meteorites don't contain zircon minerals, but they can act as similarly closed systems. And so the products of radioactive decay, such as lead, aren't leaking out of these meteorites. So here's a famous meteorite from Diablo Canyon, Arizona. You can see its center is solid metal, so it doesn't look like a rock at all. And this is an indication that it formed from an early planetesimal that didn't make it to a planet. Instead, the planet that this meteorite was originally in collided with a similarly sized object, and this exploded to bits, and this ejected it into the asteroid belt. Eventually, its orbit brought it to Earth. And the oldest of these meteorites have been dated to 4.567 billion years. And this is how the age of the Earth and the age of the solar system is estimated. So the big takeaway here is that Earth, the Moon, and the solar system all have a similar age. So the Earth and its moon were formed at around a similar time. And knowing this helps us think of good hypotheses about how the moon could be formed. And so for a while, there were two leading hypotheses about the formation of the moon. The first hypothesis, sometimes called the fission hypothesis, is that the speed of Earth's rotation was so fast that it flung the moon out from it. Now, there were mathematical models that suggested this would happen if the earlier Earth was spinning fast enough. This kind of makes me think of like a water balloon. When you throw it, it kind of splits into a figure 8 and sort of starts rotating really fast. But at the same time, a lot of people were skeptical of this argument because it didn't seem like the Earth was actually spinning fast enough for the physics to work out. The second hypothesis is called the capture hypothesis. This idea is that the moon originated from somewhere else in the solar system, but eventually orbited close enough to the Earth that Earth was able to lock it into a permanent orbit around our planet. Now, this mechanism could also be reproduced by astrophysical calculations, but it was a really delicate balance. Unless you had the perfect angle and the perfect speed, the moon would either keep flying by the Earth, or it would end up in this death spiral where it would move closer and closer to Earth and eventually crash into us. The fact that this only worked under very specific conditions made a lot of people very skeptical. The fission hypothesis predicts that because the moon formed from the Earth, it should have an identical chemical composition, whereas the capture hypothesis predicts that the moon should have a unique chemical composition compared to Earth because it formed in a different region of the solar system where the elemental composition was different. So based on rocks gathered on the moon during the Apollo mission, this can be put to the test. You'll notice that the overall composition between the Earth and the moon is similar, but the moon has a lot more oxygen and silicon and a lot less iron than the Earth. The moon also has more aluminum and calcium and less magnesium. So they're similar, but they're not the same. In addition, some of the more volatile elements, remember from the last video, these are ones that turn into a gas phase at a lower temperature. They're less abundant in the moon than they are on Earth. Examples of this are potassium or zinc. There's also less hydrated minerals on Earth. These are minerals that form and incorporate water into their chemical structure. And so this suggests that the Earth and the moon formed in very different places in the solar system. So this is evidence that the moon may have formed at much higher temperatures than the Earth. And as a result, these volatile elements, including water, were lost. So the moon probably didn't form from Earth. But what about the capture hypothesis? And to address this, we need to return to isotopes. We just talked about how radioactive isotopes can help us define the age of the moon. But there's also signatures recorded in stable isotopes that we can take advantage of. Because oxygen is one of the most abundant elements in the moon, this can be a good target, especially when samples, like moon rocks, are hard to come by. So oxygen has 3 stable isotopes: oxygen-16, oxygen-17, and oxygen-18. Oxygen-16 is by far the most abundant. It's 99.76% of all oxygen atoms. Oxygen-18 is next. It's 0.2%. And finally, there's oxygen-17 at 0.04%. So although the relative abundance of these isotopes is usually similar, it's not exactly the same. And small deviations in the amount of oxygen-17 and oxygen-18 can be used to fingerprint different chemical reactions. We'll come back to this again in the climate change module. Oxygen isotopes are a really common tool to examine climate change in the past. For instance, as water evaporates due to changing temperatures, the light isotope oxygen-16 evaporates a little faster than oxygen-17 and oxygen-18. So water vapor is enriched in the light isotope. Because there's a 2 AMU mass difference between oxygen-16 and oxygen-18, but only 1 AMU difference between oxygen-16 and oxygen-17, any kind of isotope fractionation is usually twice as big for oxygen-18 than it is for oxygen-17. In other words, the heaviest isotope is usually affected more. So in the water vapor example, there should be more oxygen-17 in the water vapor than oxygen-18. So there should be some correlation, a line essentially, between the isotopic difference in oxygen-18 and oxygen-17 when different reactions influence their abundance. So here is a figure of oxygen isotopes in the moon in these red stars. These green diamonds show oxygen isotopes in meteorites derived from Mars, and these blue squares show oxygen isotopes in meteorites derived from Vesta, which is in the asteroid belt. The oxygen isotope abundance of Earth is really well known, so it's just shown in this as this black line. So the x-axis and the y-axis represent the relative amount of oxygen-18 or 17 normalized to oxygen-16. This Greek letter delta here is just a way of expressing relatively small differences in isotope ratios relative to a known value. And this symbol here is per mil, which suggests how small these changes are. Per mil is like percent, but it's out of 1,000 instead of 100. So 4 per mil is 4 out of 1,000, or 0.4%. So you can see that these moon rocks fall exactly on the line that's found for Earth. So Earth and the moon have nearly identical oxygen isotope compositions. This is in contrast to planets or asteroids that form elsewhere in the solar system. You can see Mars falls well off this line, and so do these meteorites derived from Vesta. The fact that the Earth and the moon are so similar has been interpreted by researchers to indicate that the Earth and moon have very similar origins. So this makes it a bit hard to buy into the capture hypothesis. If the moon came from somewhere else in the solar system, it wouldn't have the same oxygen isotopes as Earth. But wait a minute, we also said that the moon has a different elemental composition than Earth. So how can we reconcile this? We need a new hypothesis. As you can see here is a computer animation of the early Earth. You can see this sort of sphere of space debris that's still accumulating as the Earth accretes. The impacts of these events are still making the Earth somewhat molten, so the crust hasn't formed yet. But then a much bigger object approaches. And hits Earth. And everything melts. So then this debris collects and eventually forms the moon. And then in parallel, the Earth and the moon begin to cool. So this is the lunar impact hypothesis, and it's currently the most favored explanation for the formation of the moon. As you just saw in the video, Earth is hit by a giant, nearly planet-sized object. Sometimes this is called Theia, but that's technically an unofficial name. Anyway, Theia hits Earth, and there's so much heat being generated upon this collision that everything melts, and the two bodies merge. But then the rotation of the Earth starts to tear them apart. All this material is re-ejected into orbit around the Earth. The different paths of these debris cause them to collide, unite, and accrete, and they form the moon. And so eventually both the Earth and the moon cool into what we know today. So is this really how the moon is formed? Well, it explains why the moon is low in volatile elements, because they were vaporized during the collision. At the same time, because Earth and the moon exchanged so much material, it makes sense that they exchanged their oxygen isotope signatures as well. Remember that most of the oxygen in the rocky planets is bound to silicate minerals, which have a pretty high condensation temperature. So it's unlikely that these will change during high temperatures because it's really hard to return these silicates to a gas phase. So at some point in time, a large amount of Earth's iron began sinking to its core, which we'll cover in a later video. But this would also explain why the moon has a lot less iron than Earth does if most of this exchange was in this sort of surface level. And so the somewhat contradictory chemical evidence has helped arrive at this rather unique and pretty amazing explanation. And while this idea is broadly accepted, at least in its major points, some of the physics of this is still being worked out. There's also been a number of new techniques to measure the isotopic composition of other elements besides oxygen. And these have been used to fine-tune questions about how exactly the moon hit the Earth and what kind of reactions happened afterwards. So in this video, we compared the ages of the Earth and the moon. We found they're very similar. This was possible by looking at radioactive decay of uranium-238 and helped by the unique chemistry of zircon minerals, which act as little time capsules. We've also shown how we can use chemical signatures to rule out hypotheses about the moon formation, how this points us towards the somewhat incredible lunar impact hypothesis. And there's one more video in this section, and it's an important one. I'll talk about how the Earth, which now is a moon, got its ocean.